Good morning, ladies and gentlemen. This is Ben Kieser with Applied Flow Technology. Hope that you are all doing well and having an excellent week so far. And I'm excited to talk to you today about heat transfer and how you can model heat transfer with AFT Fathom and AFT Aero. And it's a very useful feature to be able to clearly understand how your temperatures are changing throughout the system. And so we're going to go into great detail on that here shortly. Now, before I jump into this, what I want to do is go ahead and discuss a couple of noteworthy items. One, hopefully you are all aware that the brand new AFT Fathom automated network sizing module is available. The ANS module for AFT Fathom was launched back in May, and we have just recently launched the ANS module for AFT Aero as well. And that was officially released a few weeks ago. And so now both the automated network sizing modules for AFT Fathom and AFT Aero are now available. Where can you find more information? Well, one is on this banner on our main homepage. Simply click on View Details for the automated network sizing module. And this is where you would need to select if you are a owner-operator or if you are with an EPC firm. The reason why is because there's just slightly different messages for each of them. Give me one quick second, everyone. If any of you can hear me, please give me a virtual high five with the raise hand button on your GoToMeeting panel. So far, I've got a few high fives coming in. Okay, that's looking good. All right. Sorry, I got a message from somebody saying that they weren't able to hear me. Okay. Anyway, I'm gonna keep going here. So basically, we have this set up to where there's slightly different messaging on the specific benefits that would help owner-operators versus the benefits that would be helping EPC firms that they would be more interested in and focused on. And so you would simply click on either of those options and you'll be taken to our webpage that talks about what the ANS module does for AFT Fathom and AFT Aero. Now, obviously, there's nothing different in the software between owner-operators and EPC firms. It's the same software. It does nothing different. The only thing is the slight difference in messaging. So this is what you'll see here, and then you can go to the Fathom or Aero page. You can watch webinars on the ANS module that we've done over the last few months. And if you just want to learn more, send us an email or give us a call, and we'll be happy to give you a good demo of it. And if you want to try it out, we'll be happy to let you work with an evaluation license. That way you can take it for a spin and experience significant amounts of savings in cost and energy usage for your piping systems. So be sure to check out that page, and we'll look forward to working with you with the ANS module. All right. Before I get into talking about heat transfer, I want to show you a few useful blogs. If you go to our Learning Center on our website at aft.com, there's this tips and tricks area down here. And in the tips and tricks area, you can find all of the different blog articles that we have written to help you learn how to use the software more effectively and efficiently. And so each of these blog articles will give you a lot of good insight, and many of them come from common technical support questions. So if you just do a keyword search here for heat transfer, if I can type today, then you'll find several different blog articles that we've written on using heat transfer in AFT Fathom and AFT Aero. So this is where you can learn more information about those heat transfer capabilities. And I'm going to demonstrate for you today. All right, so when you first run, I'm going to talk about this with regards to AFT Fathom first, and then I'll go into some detail about AFT Aero. For AFT Fathom, heat transfer may or may not play a significant role in the temperature distribution for a liquid piping system. With the fluid being incompressible, the properties are going to change very little with pressure, obviously, but they're only functions of temperature. So if you are concerned about how your densities and viscosities might change out your system, especially if you have significant temperature change, then it is really important to ensure that you're accounting for those heat transfer impacts properly. Now, there's a lot of times where you could be accounting for heat transfer and it may not make that much of a difference in your results at all. And I'll show you one of those cases. So it all depends on what's going on in your system and what type of your fluid you're modeling. Now, in Fathom, heat transfer is optional. So you can do a full hydraulic system analysis without having to deal with any temperature changes throughout your system. So if you want to account for heat transfer effects, you have to turn it on. Well, how do you do that? Well, follow the yellow brick road. My favorite yellow brick road on what you need to do to build a model is the red status light down on the bottom right corner of the software. And so if I click on the red status light down here, this will pull up a checklist of items that need to be completed before you can run your model. The middle one, specify system properties, that's where you would turn on heat transfer if you're using AFT Fathom. So if I open that up, the first task would be select a fluid. Now, if you're familiar with Fathom, the blue highlighting indicates required input. So in order to do a simple hydraulic analysis, all you need is density and dynamic viscosity. Those are the only two fluid parameters that you need to specify in order to do all your pressure drop and flow calculations. Vapor pressure is also really important to specify, but it's not required unless you want to know if you're cavitating or allow your MPSHA to be calculated. But the thing is, if you look down below, there are several fluid modeling options, and you can see that heat transfer is grayed out. That's because I don't have enough information for the very simplified method to do a heat transfer analysis. So that's why you need to pick one of the other more sophisticated fluid modeling options. So let's say that I went in here and chose AFT standard. Each of these 70 different fluids are, maybe there's 70, maybe there's 50, I haven't counted them up. But there's several fluids that we've built in for you that you can work with. There's a few refrigerants as well. And you would simply select one of them and add it to the model, and then specify a temperature, and then click on Calculate Properties. So if you are using the constant fluid properties option, this is going to use these parameters in every pipe throughout the system in your model. So those values will not change if you're doing constant fluid properties. Secondly, if you turn on variable fluid properties, that will use these values as defaults, but then you can use different fluids and different pipes on a pipe-by-pipe basis. Where is that useful? Well, let's say that you have two different pipe streams mixing together, and you have fluid A in one stream, fluid B in another stream, and then your mixture. So maybe this is water, and maybe this is toluene. I don't know. This would be your water toluene mixture downstream. Well, variable fluid properties allows you to specify each individual fluid in each individual pipe. So if you open up any of these pipes, you would see a fluid data tab where you can pick which fluid you want to use in that particular pipe. So you can do this mixing if you know what the mixture composition is. As long as you know what the mixture composition is on a mass or mole fraction basis, you can specify that right here in this pipe directly, and then we'll do all the calculations for you. So the key thing here is when you specify the different fluids and different densities, we will be balancing the mass across this mixing junction right here to ensure that you are in mass balance. So that's where you would use variable fluid properties. However, if you are wanting to do a poor man's approach to heat transfer, maybe you don't know all the heat transfer information, but you know the temperatures in your different pipes. Well, if you just want to specify your temperatures in different pipes directly, then the variable fluid properties option allows you to account for the temperatures that have been changed due to heat transfer without having to do all the extra heat transfer calculations. So it's a bit of a simplified method in that regard. Let's see. Okay, so now I'm going to go ahead and turn on heat transfer. Sit tight, everyone. I'm having some technical difficulties here. I'm going to pause things. Hang on. Testing, testing, testing. Everyone, again, if you can hear me, give me another hypothetical virtual high five with the raise hand button. Okay. I'm getting several high fives. Casey, I apologize. I'm not sure what's going on. Let's see. It seems that everyone else can, or a lot of people can hear me. Okay, it's fixed now. All right. Good. Sorry about that. I don't know what the deal is. Okay, I'm going to go ahead and keep on going here. And if you have any questions, let us know. All right, so how do you turn on heat transfer in Fathom? You would select one of these two options right here to use heat transfer with energy balance, single fluid, or heat transfer with multiple fluids. There's different situations where you would use those different options, and I will go into both of them. And the first one I'm going to do is the easier one, heat transfer with energy balance, single fluid. So I've turned that option on. Once you do that, that will allow you to model heat transfer. If you drag and drop a pipe on the workspace and open up your pipe, you'll see that there's a new heat transfer tab in the property window. By default, it's going to use an adiabatic thermal model, so the piping is fully insulated, but there are several other heat transfer methods that you can work with, either constant temperatures, but again, that's not really all that exciting, but you'd want to maybe do a convective heat transfer thermal model. So if you are losing heat to the ambient conditions, then convection is what you would want to use, and you can specify the temperature and wind speed of your ambient conditions. Why is fluid velocity needed? Well, the answer is because in the latest version of AFT Fathom and AFT Aero, we now have correlations built in for calculating the external heat transfer coefficient for you, which is a really handy thing. So if you were to click on this drop-down menu here, we can model either forced convection or free convection. And so these are the convective thermal models built in to calculate your heat transfer coefficient, and that's why you need a fluid velocity. Essentially, it's your wind speed. And you can have your pipes either submerged in air or in water at this point in time. So those are your options. If your fluid is not in air or water and the properties are very different, Or if you don't want to use the correlation, you can go back to the old-fashioned way by doing a user-specified thermal model, and that way you can have the temperature simply be specified where you're entering your convection coefficient directly. So that's what we have for the convective thermal model. Now, what I'm going to do is I'm going to go ahead and open up one of our pre-built models, and I'm going to demonstrate some more heat transfer stuff with that. All right, let me open this up here. Okay, so this is one of our examples, and I'm going to do the GSC. So here we have a very simple piping network, and the fluid that we are modeling in the system properties window is simply water, and we are using the heat transfer with energy balance option. Now, one thing I want to point out is when you pick heat transfer, you still have to specify a temperature and calculate the properties. In the end, those values are not going to be used. It's reference only. So really, you could specify whatever temperature you want, as long as it's between these boundaries here, and it doesn't matter what you do, because ultimately your pipes are going to pick up their physical property changes based upon the temperature change throughout the piping system itself. So now that heat transfer is turned on, where do you specify your temperature reference to start the calculations? Well, that's going to be done in your boundary conditions. So if you're turning on heat transfer, for each of these boundaries, you have a reservoir where you would specify a liquid height and a surface pressure. You would have a assigned pressure maybe, and that's where you define a fixed pressure or a fixed flow rate. If you're doing heat transfer, each of those junctions require a new piece of data, which is your temperature. So if I'm using the reservoir junction, like how I am in this particular model here, and I open up the reservoir, this is where you would need to specify what your liquid temperature is. So this is the temperature that gets fed into the piping. So my temperatures are starting off in this piping system at 200 degrees Fahrenheit. And this box is important because you'd want the density inside your reservoir to change with the temperature of the reservoir. So that's where you'd specify your boundary temperature. So I've got that specified. And then in the pipes themselves, if I open this up, I thought I opened it. This pipe is using an adiabatic thermal model. Same with this pipe. Same with this pipe, same with that pipe. All pipes are using adiabatic for their thermal models right now. So this is, again, a very simplified situation. Now, the only thing that's changing heat transfer, or that's causing heat transfer and temperature change, is these heat exchangers right here. So if you're modeling heat transfer, you can model heat transfer in 3 different types of objects. Either pumps, where if you have a inefficient fluid, or if you have a very inefficient pump, you can transfer that pump inefficiency to your system fluid as a heat input. You can also model heat transfer through heat exchangers and heat transfer through pipes as well. So right now I'm going to go ahead and open up this heat exchanger. And if you go to the thermal data tab, there are 11 different thermal models in this drop-down menu that you can use. 5 or 6 of them are really simplified, and then the others are a bit more sophisticated. Let's talk about the simplified ones first. Controlled downstream temperature. This is probably one of the best thermal models to use if you don't have any other information about your heat exchanger, because all you need to do is specify the temperature at the outlet of your heat exchanger, and then Fathom will calculate the required heat rate across your heat exchanger needed to give you that temperature. That's all that it is. And so it's a very simplified method, and it can help you potentially size your heat exchangers. or if you have a spec sheet, you might have other tools that are more sophisticated for heat exchangers, and this will give you a good sanity check if you're actually getting the actual temperatures and heat rates to correspond with what you might have calculated in the other tools. And if they're not, then you might have an issue with how you're modeling your system. So that's one of the simplified methods. The other simplified methods, you can do a constant heat rate, which is this one right here. I would not necessarily recommend using this one all the time. You can use it, but what this does is it turns your heat exchanger into basically an assigned heat transfer junction. Here's where this can potentially cause an issue. You have your heat transfer, which equals your mass flow rate times your heat capacity times your change in temperature across that heat exchanger. You're specifying your heat transfer, your mass flow rate, and your heat capacity are calculated from your system conditions. So what is your delta T? Well, that temperature change is going to be whatever it needs to be in order to satisfy this equation. The reason why this is important to be careful of is because you might have a delta T that is very unrealistic. If it's requiring a temperature change of 1,000 degrees in order to satisfy that equation, then perhaps something is not specified right in your model. So if you're going to use this particular thermal model, make sure that your temperature change is realistic, okay? That's very important to do. Also, it could potentially cause convergence issues if you have very large temperature differences, which if it causes your fluid properties to stumble into a saturated region, then that would be a major issue where the model may not be able to converge. So if this thermal model actually works, just be sure to check the temperature change to make sure it's realistic. Now, the sophisticated methods are a bit more fun. So let's use a counterflow one, for example. If you're doing any of the heat exchanger models that uses the effectiveness NTU methods, then there are some more parameters that you would need to specify. Heat transfer area, your overall heat transfer coefficient, that's the blue highlighting, that's your required input. Now, what is the secondary fluid data? The secondary fluid data is the fluid on the other side of the heat exchanger. As you can see in this particular model, I'm only modeling one side of the heat exchanger because you can only connect 2 pipes to a single heat exchanger junction. That's the most pipes that you can connect to heat exchangers is 2 pipes, which will be specified right here. Not 4, only 2. So here's where this method is really nice, is because this field down here allows you to account for the heat transfer impacts of the other side of the heat exchanger without having to have that explicitly modeled in your system. So all you need is flow rate, specific heat, and inlet temperature of your fluid on the other side of the heat exchanger, and it will take into account all of the heat transfer impacts for you. The other reason why that's really helpful is maybe the other side of the heat exchanger might be a gas. Well, in Fathom, you model liquids, not gases, and so that's where this would be really helpful, because you can account for your heat transfer impacts from the gas on the other side of the heat exchanger unit. So those are the different thermal models that are available. Each of these counterflow, you have to specify the same input information. As you can see, when I'm changing to any of these different thermal models, the input that you have to specify is exactly the same. So that's why it's simple enough to talk about this in terms of simplified methods like the controlled outlet temperature, or one of the fancy ones that uses the effectiveness NTU methods. Hang on one second. Apologies for that. Just had to rehydrate really quick. And uh, as my throat gets really dry when I keep talking. All right, so what are we doing here in this example? We are taking 200-degree water. We are flowing it across a heat exchanger where the inlet of the other heat exchanger is at a temperature of 40 degrees Fahrenheit. So we're trying to cool down this really hot water, and we're using the heat exchangers in order to do that. Now I have a specification where by the time that all my system flow reaches this location, I want that temperature to be 120 degrees Fahrenheit. So there's a really useful option that helps you quickly be able to do that. That's with the goal seeking control module. So right here, I'm modeling a three-way valve junction, which is this junction right here. And if I open up that junction, it allows me to split my flow in different ways. What you would do is specify your CV versus open percentage for each leg that you would be splitting the flow to. Now, I've just done a very simplified estimate of 100% open and 100% closed and a fully open CV of 100 on each leg. And it's linear. You could have something that might be a lot more sophisticated and a lot different. So, but this is how I'm modeling the three-way valve in my system. So I don't know what the actual open percentage is. I need to change the open percentage to achieve a temperature of 120 degrees right there. So I'm going to use the goal seeking control module to do this for me. That way I don't have to do any of that manual iteration. So I already went to the button right here next to the status light to turn it on. So if I click on that button, you can see that the goal seeking control module is enabled. So if I go in here to analysis and then goal seeking control manager, this is where you define your goals and variables. So the thing that I'm changing in this system is the three-way valve open percentage for my three-way valve junction. You can put upper and lower bounds. It obviously has to be between 0 and 100. It can't go outside those boundaries. And then my goal is to achieve a temperature of 120 degrees at the branch junction right here at J8. So let's go and see if we can accomplish this. All right, so I'm going to go ahead and run the model. And as you can see, with all that iteration that it needs to do, it's doing it very, very quickly. When you're doing heat transfer, there's so many variables available for the GSC module where you can do some really sophisticated stuff. If you don't know what your heat exchanger heat transfer area is, for example, if you're trying to size your heat transfer area, you can set that as a variable. So if you don't know what it is, set it as a variable to get the overall temperatures that you want. There's a lot of flexibility that you have with the GSC module. Now let's break this down really quick. I have a warning message that tells me HGL, EGL, and head loss results may not be meaningful for variable density systems. The key thing is whenever you see a warning message or a caution message, you should read the message. If you read the message, it's going to tell you what the issue might be. And then if you pay attention to the top, it says if you select a message and then press the F1 button on your keyboard, what that will do is it'll bring up our help file where you can find that particular message in here. That way you'll be able to read more discussion on what that warning message is actually trying to tell you. So what is this telling me here? Let's examine the HGL, hydraulic grade line. Well, your hydraulic grade line is equal to your pressure divided by the density times gravity, make that look a little bit more like density, plus the local elevation at that location. So as you can see here, the hydraulic grade line depends on what the density is. If you have a temperature change inside of a pipe, So you have T1 here and T2 here. Your density is going to be different at each of the ends of the pipe as well. Well, what we're doing is we're calculating an average density inside Fathom. So when we're doing heat transfer in the pipes, we're calculating an average density, and if you were to substitute that in right here, it may not calculate an accurate hydraulic grade line. Same thing for energy grade line or head loss. So that's what this message is telling you, is that those three parameters, they have a density dependence, and if your density is changing inside the pipes, then you might not want to be using those parameters. So here's how I can get rid of them. If I open up the output control window, which is either this button right here or this button right here, it's the little spreadsheet tool that has a pen on it. This is where you can dictate which parameters are shown. So for my pipes, as you can see, I've got head loss. So this is one of those parameters that has a density dependence, and I don't want to be bothered with that warning message. So I'm actually going to go ahead and remove that parameter and click OK. And once that finishes loading, look, no warnings. Well, why don't I have any warnings? It's because I hid the warning message relating to head loss, because that's not going to be what I'm focusing on anyway. I'm going to look at pressures, temperatures, flow rates, velocities, etc. So that's the what I wanted to discuss as far as warning messages. Now let's take a look at the valve open percentage. If I go to the GSC variables, the valve needs to be 85% open. That's where I'm allowing the majority of the flow to go through the heat exchangers. So 339 gallons per minute versus 73 gallons per minute. So how do I know that my goal was met? Well, if I go to the goals tab, it's 120 degrees Fahrenheit. So let me add on some temperatures into my pipes. So if I add my temperature inlet and temperature outlet, I can know what my temperatures are. I'm also going to get rid of a few other parameters that I don't care about. I'm going to get rid of the name of the pipe because it's just called name. All right, so let's zoom in here. So I've got 102 degrees Fahrenheit after the heat exchangers. And then in this particular pipe right here, I have 200 degrees Fahrenheit. Well, here's the awesome thing about AFT Fathom, is that we're going to do an energy balance around all of your junctions in your system to make sure that not only is the mass balancing, but we need to make sure that the energy is balancing across them as well. So if I take a look at the temperature downstream, look at that, 120 degrees Fahrenheit. So I've got 102 degrees coming in for pipe 8, and then I have 200 degrees coming in for pipe 9. When those two mix together, I get exactly the temperature that I want of 120 degrees Fahrenheit, and this three-way valve has to be at least 85% open. Now, I'm not doing any piping heat transfer, okay? Let's say that it was a very hot day outside. I want to do some convection. So what I'm going to do is I'm going to go to the edit menu, and then I'm going to go down to global pipe edit, and I'm going to throw on some convective heat losses there. Now, when you're doing a global editing operation, the thing I want you to remember is that this is just causing your property window to be a template window. So the thing is, you only need to specify what you actually care about specifying. The minimum required input is inner diameter, length, and friction model. But if you only care about heat transfer, you don't have to specify any of that stuff. So if I went straight to the heat transfer tab, all I need to do is turn on convective heat transfer, and then this is all I need to specify. But here's the thing: look at the resistance layers. Okay. I've got my internal fluid correlation. That's where you can use either the Dittus-Boelter equation or the Nolinsky equation for your internal convection coefficient. Then you have conduction through the pipe wall. Well, here's the thing about global editing. When this is a template window for your global editing operation, if you don't have a material specified, then it's just going to do a user specify where you'd have to specify conductivity and thickness yourself. I don't want to bother with that. So if I went back to the pipe model and change this to the pipe material that I'm using in my system, I can now go back and take advantage of using the thermal conductivity that's available in our pipe material database, as well as the wall thickness. So that's less information that I have to specify. So if I have convective heat transfer losses going on, the only thing I need to do is set the thermal model to convective heat transfer. You can do layers of insulation if you want. You can do up to 3 different layers of insulation, either externally or internally. If you do internal insulation, it will reduce your inner diameter in the piping. Here, I'm not going to do any insulation. So let's say that it's a really hot day outside. Let's call it 105 degrees. Thankfully, we don't get that hot here in Colorado Springs. If it's a lot hotter where you guys are in the webinar, I hope you're finding ways to stay cool. Next is going to be my wind speed. Let's say that I have a average wind speed of, 10 miles an hour, a nice little breeze. And then I'm just going to accept the default stuff down here, and I'm going to allow my convection coefficient to be calculated based upon the correlation. So I get all this information specified, I click OK. This is where I check the boxes on what I want to specify as changes to my model. So the only thing that I care about changing is the heat transfer parameters. So even though I set the pipe material in order to get the wall thickness, I don't have to accept those changes. I just had to set it so that it picks up the database here. So that's why I'm only checking the boxes for heat transfer related things. Click Apply Selections, click OK. Let's do some spot checks. Let's open up this pipe. Well, now we've got heat transfer. And as you can see, this brought over all my information, and it has the appropriate wall thickness based upon the diameter of this particular pipe, which is 7.981 inches in diameter. So that's where I just had to change the material with global editing to get it to read the database for the pipe wall conduction layer right here. If I right click on the rest of these and spot check, I can see 105 degrees, 105 degrees. Let's open this guy up. 105 degrees, 10 miles an hour. So everything is all set up. Now I'm going to run my system with that external heat transfer. I'm going to see if it changes my results any as far as the valve open percentage. Now, you can see here that this is taking just a little bit longer to converge. Well, when you pile on heat transfer to a relatively complicated piping network, it makes your calculations that you have to do even more complex. And so those heat transfer calculations are highly complicated, as well as getting the energy balances all throughout the network, and the new correlations for that heat transfer coefficient adds more complexity to the system as well. So this is why sometimes when you're using these more sophisticated methods, it's going to take your Fathom models to run a little bit longer. But again, would you rather have this, or would you rather be scratching your head and struggling over trying to type in those big, long heat transfer equations into spreadsheets, hoping that you type them in correctly and not have any mistakes? All right, so we've got some results here. Let's take a look at what's going on. Okay, so if I go to my GSC variables, look at that, 85% open basically. So the open percentage didn't actually need to change very much at all in order to get my desired temperature of 120 degrees Fahrenheit. But let's see how things are changing in the system. As you remember, I had 200 degrees coming in. So this is a 20-foot long pipe. When it's sitting out there in the sun, it's dropping by 1/10 of a degree. So that's not very much temperature change at all. Same thing here, hardly any temperature change. But what about this pipe? This pipe is 200 feet long, so it's a little bit longer. It's dropping by 3 degrees Fahrenheit. So when it drops down to 3 degrees and it's at 78 gallons per minute, it has to push a little bit more into that system in order to give me the temperature that I want of 120 degrees. So as I mentioned before, it depends on the kind of system that you're dealing with. If you have a liquid system and you're just modeling water, your temperature change in the pipes probably will be very small, unless you have very long runs of pipe or smaller diameter pipes. The larger your pipe diameters, it's going to retain whatever temperature is coming in at, and it's not going to change very much. So, but it's definitely something you would want to look at. So that's how you can model heat transfer inside the pipes. There are some additional piping heat transfer options that are new. And so we have this convective heat transfer with heat tracing. So if you have electrical wires or maybe steam piping wrapped around pipes that is adding some heat to your piping heat transfer, you can model that as a heat flux. If you want to account for solar radiation, you can use convective heat transfer with a heat flux. So you just convert your radiation to a heat flux value and specify that indirectly. If you have buried piping, we now have a buried pipe thermal model that you can work with. So if you do a buried pipe, this is where you would specify what your soil surface temperature is, what's your buried pipe depth, and then your soil conductivity, and that will allow your buried piping to be modeled accurately with regard to heat transfer. Now, let's take a look at what that other heat transfer option was. This is all system fluid in one single model right here. So if I go back to my system properties window, heat transfer with energy balance, single fluid, it's only one fluid in my system that I'm dealing with. Let me open up something that's a little more complicated. Let's see. Give me 1 second here. All right. So now that this is going to be opening up my new system, this is where you would use the heat transfer with energy balance, multiple fluids, the bottom option. This is a really cool capability. So what I have here on one single workspace is two completely independent systems. I've got my cooling water loop on the left-hand side, and I've got a hot oil loop on the right-hand side. So that's what I have in my model. Now, these two heat exchanger junctions right here, those actually represent the same physical heat exchanger in reality. Okay, so the cooling water that flows through the tube side of the heat exchanger, and then I have a hot oil mixture which flows through the shell side of the heat exchanger. So the reason why it's really helpful to use the multiple fluids option is it allows you to model both sides of the heat exchanger in a single model, as well as including their respective loops on the same workspace. This is called thermal linking. That means that these two heat exchangers are thermally linked together, where the heat from the hot side of the hot oil is going to heat up the cold water flowing through it. And that's how I have heat transfer being shared across those two heat exchangers. So here's the process of what you would do to set this up. Same thing as usual, follow the yellow brick road with the checklist items and the status light. You would build your entire model of your system with laying out all of your pipes and junctions, define your input for all your piping and all your components, your pump curves, your reservoir values, etc. And after you build your system, what you're going to do is you're going to create some groups. You would create a group with all of the pipes and junctions for the cooling water loop, and then you would do a separate group for all the pipes and junctions in the hot oil circuit. So once when I've done that, you would select these pipes and junctions, go to Edit, Groups, and then Create, and that's how you can create a group. I already have those groups created. So if I open up my Select Special, I'm going to select the cooling tower circuit. So as you can see, I've already done that. If I go to my groups and then Group Manager, you can see I've got my cooling tower circuit. When you select that group, it selects the appropriate pipes and junctions that are in that group. If I switch it to the hot oil circuit, you can see how it changes up the selections for me. After you've gone through and you have selected your groups, this is where the multiple fluids comes into play. As I mentioned, when you're doing regular heat transfer, even with the single fluid option, these values don't even matter because you're specifying what's in your boundary conditions. But when you're doing the multiple fluids option, that's where you need to do one more step. Excuse me, that's where you need to do one more step. This is where you specify which system is using which fluid. So if I go back to Edit and then Groups and then Fluids, this is where I pick which group is using which particular fluid. So as you can see, when I am in here, you would click on these little buttons, and that's how you select a fluid for that particular group. So if I do the first one, here's something that's really neat, is that I can use an AFT standard fluid for one particular group. Again, this stuff doesn't even matter. So you can specify whatever values you want. All that I care about is water. The reason for that is because when I go back to here, after I've told the cooling tower circuit to use water as my fluid, I specify my inlet temperature coming in at the reservoir, and that the temperatures will change throughout the system based upon heat transfer. Then I also have my hot oil circuit. Now this is really neat, is because my hot oil actually uses a mixture using the Chempack fluid. So when you're doing the multiple fluids for heat transfer, you can actually mix and match the different fluid models that you want to use. So you can use both AFT standard fluids and Chempack fluids and RevProp fluids all in the same system if you want. This hot oil mixture here that I have uses hexane, heptane, and octane. I made that up. And then again, these values don't matter because you're specifying your boundary condition in the boundary junction, which is this guy right here. So here's what we have going on. We have cooling water coming in, and that temperature coming in is going to be, what is it? 40 degrees Fahrenheit. So we have 40 degree Fahrenheit water coming in, and it's circulating throughout the system. And then we have this bypass, and we have a three-way valve here. This is where you can get even more fancy and sophisticated by using GSC again to really control your temperature. Let's say that your spray nozzles were sensitive to temperature, and you want to make sure that downstream, maybe you need a temperature of like 60 degrees or something. this bypass can help you control that a little bit more efficiently than just guessing and checking. Then on my right-hand side, I have hot oil that is circulating around the loop, and this is heating up the cooling water circuit fluid. Now, the last step that you need to do for the multiple fluids option is you have to thermally link these two heat exchangers together. How in the world do you do that? Well, if you open up the heat exchangers, you would go to the thermal data tab. When you're doing this thermal linking capability like this to get this dotted blue and red line where it's representing the same physical heat exchanger with two heat exchanger junctions, you have to use one of the sophisticated methods. One of the thermal models that is a effectiveness NTU method. So that's a counterflow. That's where it makes you specify what your heat transfer area and your overall heat transfer coefficient is. But then you would click on this option to link it to another heat exchanger in your model. After that, what you would then do is go into the other heat exchanger right here, and you can see how that is just linked back to the previous one. And so now these two heat exchangers are thermally linked. They will share heat transfer with each other. Now this heat exchanger over here is one of the models that is more sophisticated. Actually, no, it's not. I lied, sorry. This is using just a simplified 150 degree temperature. So I've got 150 degree temperature that I want in my pipeline for the hot oil mixture to be fed in, and then we'll see how things transfer heat with each other. So let's go ahead and run the model and see what the results look like. Okay, so if I go to the heat exchanger summary, let's take a look at that heat rate. As you can see, we have 1,782 BTUs per second of hot fluid that is transferring heat to the cold side, which is the cooling water loop, 1,782 BTUs per second. So those two heat exchangers are thermally linked together. Now, if we look at the temperatures here, we can see that we've got 40 degrees Fahrenheit coming in, and then afterwards we have 68 degrees Fahrenheit. On the other side of the heat exchanger for the hot oil loop, we've got 150 degrees coming in, and it's leaving at 73 degrees. Now, I am doing convective heat transfer, I believe, in my pipes. Let's check. Yes. So for the majority of all my pipes in my system, it's a moderately cool day, 65 degrees, that's nice. And I've got a heat transfer coefficient in there. So I do have some convective heat losses going on in the system. So this is where I would do some graphs to be able to see my temperature change throughout the profile. So what I'm going to do is I'm going to select these pipes right here. Just like that, and I'm going to create a group. I'm going to go to Edit, Groups, and I'm going to click on Create Cooling Path 1. And then what I'm going to do is I'm going to select some pipes on the right-hand side. It just has to be a continuous flow path. Edit, Groups, Create, and I'll call this Heating Path 1. So now that I have results, I can go to the graph results window and I can plot how the temperature changes through each path. So if I do profile, I can click on this plot single path, and I'm going to plot multiple paths using groups. So let's look at the pressure and let's look at the temperature and the pressure. So I'm going to move this up and call it temperature and pressure. Let's go ahead and also take a look at what the surface temperature is. Okay, so why does this look so skewed? That's because one system has a lot more piping than the other system. So this is not the greatest way to do it. I've already plotted. Let's look at the cooling tower circuit first. So here's my cooling tower circuit. This is the flow path around the cooling tower all the way through the lower pump down below. So I'm looking at the temperature and pressure. And as you can see, the temperature change is very, very small all throughout the system. And the only area where you have significant temperature change is obviously at the heat exchangers. But what does the surface temperature look like? Let's go ahead and add that in there as well. So I'm going to add another parameter. It's the bottom one right here. I'm going to call this surface temperature, and then I'm going to move him up and then to the right. So I'm going to indent this guy to the right. That creates a secondary y-axis. So my secondary y-axis over here, the red, or that should be a red line. Looks like it's blue and purple. And as you can see, the surface temperature is very close to the fluid temperature. So that's plotting those two things together. The hot oil circuit is very similar, where you have hardly any temperature change in the piping. The place where you have your temperature change is mainly at the heat exchanger, but that just happens to be the way that it is for this particular system. You may have cases where your temperature change in the pipes is actually very, very significant, and you want to make sure you capture that in the models, and Fathom will do that all for you by itself. All right, so that's heat transfer with AFT Fathom. Now, AFT Aero heat transfer modeling is the same exact process. Okay, so let me open up an example here. So you would specify heat transfer in the same exact way. I don't have any heat exchangers in this model, but if I was to put one on the workspace, look at that, same thing. Controlled downstream temperature, we have effectiveness NTU methods, so on and so forth. So you can do the same, other side of the heat exchanger model, you can do the same thermal linking ability in Aero. The piping heat transfer is the same. So if you open up one of the pipes, you've got the same options. All of these are available, and you can allow your external heat transfer coefficient to be calculated by the correlations if you want, where you would need to enter a wind speed. But here's the main difference between Fathom and Aero in regards to heat transfer. In the system properties window in Aero, you do not have to turn on heat transfer. Heat transfer is always being calculated for you no matter what. The reason why is because heat transfer is a very important aspect of compressible flow modeling. So it's always doing heat transfer calculations. Now, by default, it's going to use adiabatic for the thermal models in your pipes, but even with adiabatic pipes, you will still have temperature change due to compressible effects. Because gas is compressible, when it flows down a pipeline, your pressure is going to decrease. As that pressure decreases, your temperature is going to go down. So even when you have an adiabatic thermal model, you still got temperature change in your system in Aero. And Aero will be able to capture all of that for you. And so it's a lot more exciting because your temperature changes will a lot of times be nonlinear. So let's go ahead and run one of the models here, and we'll see how the temperature changes throughout the system. All right. So what I want to do is I want to plot the temperature change in this flow path to the furthest remote tool. So I go to Profile, and select temperature, that temperature change is a lot more significant for a gas piping system than you will see for a liquid piping system. So when you're dealing with gases, it's very, very important to evaluate your heat transfer properly. Another reason is because your heat transfer will have an impact on your system flow rates. There's a technical paper that I want to highlight to you all on our website. If you go to the Learning Center under Technical Papers and scroll decently far down, it's this one right here called Gas Flow Calculations Don't Choke. If you open up this paper, this is an awesome article for Chemical Engineering Magazine back in 2000, and this talks in really good detail about the fundamental thermodynamic equations that you need to use in order to properly account for compressible flow. If you're not doing that, or if you're doing incompressible flow methods, there's going to be some significant uncertainties in your system that you're just not going to know for sure if you're getting the right answers. And Arrow will, because it's using thermodynamic equations. The reason why I wanted to highlight this is to take a look at this particular plot. This graph right here, it houses 4 different cases. It shows you the temperature profiles in a pipe for a case where the gas is heated, where it's cooled, and then adiabatic and isothermal. The reason why that was done is to see if adiabatic and isothermal assumptions bracket all potential conditions. Well, for the temperature profiles, you can clearly see that that's not the case. If you're heating or cooling a gas, you can see how that temperature change is very different than the so-called maximum or minimum conditions, which is just dead wrong. The other thing is, if you take a look at the flow rates here, the case where the gas is cooled is the highest flow rate, and the case where the gas is heated is the lowest flow rate. So that's the other important thing about paying attention to heat transfer with AFT Arrow, is that your heat transfer impacts will be much more significant than typically in liquid systems, and it will very much change not only your temperature distributions through your system, but heat transfer will also make an impact on your pressure and flow distributions. And Arrow will handle that all by itself for you. You don't have to do any of your own energy balances. Arrow will handle that all by itself. All right. That takes care of today's webinar. Thank you all very, very much for listening in. I hope that you all explore the heat transfer capabilities in the software more that has been introduced now. We have some examples in our walkthrough tutorials in the software. So if you're not able to remember, just do this. Go into Fathom or Arrow, and then under the Help menu, click on Show Examples. And this is where you can find all of our walkthrough tutorials that will teach you about how to use the software in different ways. As you can see, for Fathom, there are several examples. So if you want to learn how to use heat transfer, there's 2 examples. There's the heat transfer example. This is a very, very, very basic one. And then there's another one, which is a Freon delivery system. And then there is the third one with the goal sync and control module example. So if you go to the goal sync and control module, this is the one that I demonstrated today, where you're using GSC to control that through a valve position. So definitely explore those capabilities. These example help files will help you learn how to use heat transfer. And then I want to see your case studies. Send us your systems where you've been able to accomplish great things with the software. We have tons and tons of excellent case studies on our website that shows how people were able to do wonderful things with their system and improve reliability and solve problems. And these are all available. And so we have a contest each year. If you go to About and then Platinum Pipe Award, this is where you can submit your work for our contest in different ways. And so if you win, you'll win $2,000 for your company and a $500 Amazon gift certificate for you. And so even if you have a system which is very proprietary and confidential, that's fine. We can work with you to help you figure out how to change your system and remove all the stuff that's confidential to where it still tells the story of what happened. And that way, others will be able to see if you're able to match your model results to actual measured data, or if you're able to increase operational benefits and sustainability, or just we want to see your creativity. So send that to us. You can apply for our Platinum Pipe Award online and send it, and we'll be able to get a case study out of that. All right. Thank you all very much for your time today. Take care and have a wonderful rest of your week.